Hi, Philip. Welcome back. Hey, Frank. Welcome. All right, welcome back. Hope you guys are all doing well. Hopefully you guys enjoyed that day off from chem class yesterday. Hope you took advantage of that weather, and hopefully you guys are staying safe too. A couple things. It's going to be a really nice day out today again, so please go outside eventually after you get done with your schoolwork. Go outside, go for a walk, jog, whatever it may be. It's going to be nice today. It's going to be cooling down the rest of the week, so take advantage of what we have. Looking for a couple people. Look for Leo, Joey, and that's it. Joseph and Leonardo. If you're here, please let me know. Please unmute or throw your name in the chat. Bunch of things for housekeeping for today. As you know, I think I told you this last time. As you know, we are, middle school is going back on the 22nd. Middle school is going back on the 22nd in 2 different cohorts. Hopefully your parents have information for your younger siblings. Additionally, that week is when the elementary school will obviously, they'll do Monday, Tuesday, but Wednesday is going to be a day where they could go back as well. More information. I was listening to the Talk of the Town radio show the other day when Mr. Karam was our superintendent, was on for an interview. And he did say that he is planning on us returning. It's not official yet. He's planning on Proctor returning a week after middle school's rolled out. So he said it to the community. It's not official yet, but he said it. He's planning on that date or maybe a week after. So maybe the 29th will start the rollback plan for Proctor. Maybe the week after spring break. So spring break's going to happen at the Friday the 2nd we have off. And then you have the whole next week off as well for spring break. Maybe it'll start after spring break. Maybe it's a week before. They're kind of ironing out the kinks. Not sure, but it's probably going to happen one of those weeks. Additionally, he did mention he is planning, and we are planning on participating in spring sports. That's cool. Hey, Leo, try to get here a few minutes earlier. So spring sports are planning on rolling out for, obviously, when we get back. Hopefully you do. It's been like a whole year of lost athletics. Almost a whole year of you guys being in Proctor. Crazy. But we're getting closer. We're getting closer. Does anybody have any questions on random stuff like that? It's not official. Sports are not official. It wasn't approved by the board. But he did mention that he plans to bring that back. If I hear any more information, I will definitely relate it to you. Once it becomes official, I'll definitely communicate it with you as well. Let's check out the COVID report, see where we stand for today. So as you're noticing in the community, there's more and more things opening up. Restaurants could open up at 75% capacity. Cool. More and more things are opening up. Recreational things are starting to roll and open up. We have 484 active cases of COVID in the county. We have 18,831 resolved cases of COVID. Big number. Cool. That number has definitely decreased a few more. The number of deaths has remained the same. Last 4 days, last 5 days, we haven't had any more deaths. Another good sign. Hospitalization numbers have been consistent last week. And then really what's happening now, we're vaccinating a lot more of the population. So the more people that are vaccinated in the community, the better off we'll be. The more we'll open up, the more normal we'll be again. So all that information is given to you. Let's check out the number of daily positive cases of COVID. Where do we stand? On the 8th, we had 32 cases, below 40. Remember, that was our goal, my mental goal. Below 32. The The 7th, we had 35, 32. So it looks like we're hovering mid-30s, over 30s. As long as we're below 40, I see things opening up more and more and more. We don't want to get to something like that again. Additionally, Governor Cuomo came to Syracuse Airport, and he came to the state fairgrounds yesterday. He just said that the state fairgrounds gave out the second most vaccines in the county. Big thing. They're giving out a lot of vaccines. That's good for us because they're a neighbor community with us. I know you think Syracuse is so far away, but they're relatively close to us. If someone has COVID or contracts COVID, numbers are bad at COVID in Syracuse, it could easily travel over to our county. So people work in Syracuse, people commute back and forth. That's good. Our neighbor communities are getting vaccinated. Hopefully, they'll really take off here as well. All right, moving on forward. Let's see what's going on for Chem class, best class of the day. Your 5-week report is going to be due Friday. Hopefully, you guys know all your grades were supposed to be completed by last night. I'm finalizing the grades, and next week I'll probably do like a breakout room. I'll take each one of you guys and I'll ask if you want to see your grades. I'll show you them, but there's really not too many surprises if you do your exit passes when you do that. One thing that I'm noticing on Google Classroom is your grades. If your grades up here, if you go to your grades, if you could even see them, I don't know what you can see still. If you could see your own grades, that grade is not going to be the exact same grade as what I have in my grade book or what School Tool generates or the average that you have. Why? Because within the grades, there's going to be like the warm-ups. There's going to be all these other assessments, the examples that you turn in, all these other things that I do not add towards your overall grade. What goes towards your overall grade, and a lot of you guys are doing really well, your guided notes, huge. If you do your guided notes, you're in good shape. Well, I'm talking about guided notes. Most of you guys are doing an awesome job with that. Awesome. But some of you guys are just like logging into the Zoom session and you're not filling out your notes. I don't even get it. I don't get why you're even wasting your time or my time if you're going to sit here for 84 minutes or pretend to sit here for 84 minutes and not do anything. If you do your guided notes, you pay attention a little bit, you understand the guided notes, you're paying attention, and you understand the examples, the exit pass should be a breeze for you to do. Ask a majority of your classmates. If you're doing the work, you're trying it out, then you're doing pretty good in this class. If you're just logging into the Zoom screen saying, peace out, Mr. Brown, you're probably not going to do too well. But anyways, I'm grading your guided notes. I'm grading your exit passes, several exit passes. You know there's an exit pass for every topic that I assign. And table I, that's it. Those are the things I graded for the 35-week period, the 5-week period. Again, if anybody has any questions, please feel free to let me know. I will finalize those grades. Some people ask about their grades or grades or grades. You finish your exit pass and you want your grade automatically to you. It takes a little time. So I will get those grades to you. We'll do that next week. Plan for that next week. If you email me, I'll email you back. If you email me about obviously something, I'll definitely email you back on that too. Just take some time. All right, so what's happening for today? Here we go. Get out and enjoy this weather after the best class of the day. Quote of the week comes from Albert Einstein. The people who think they are crazy enough to change the world are the ones who do. Get crazy. Get out there, change the world. Make a difference. Today's Wednesday, March 10th, 2021. Today's the day 4. We are continuing on, and we'll finish up Kinetics and Equilibrium this week. We definitely will. Next couple classes are going to be a little challenging for some people. Le Chatielers and Equilibrium, the concepts of that, the examples for that, they take a while to really understand. So brace yourself for today. Equilibrium, Le Chatielers, we're going to go through a lot of examples next class, especially on Le Chatielers, where it's going to take some time to go through, but you'll understand them, hopefully, most likely, at the end. So here we go. For today's class, we're going to wrap up equilibrium. We'll watch YouTube flick on dynamic equilibrium. We'll go through some examples, and then we'll make sure I have the notes there. And then you should be able to do the exit pass concluding the examples. Then we'll move on to Le Chatielers principle, watch another YouTube flick. We'll go through the notes, and I'll wrap up with a different video at the end. So 3 videos today, examples, examples, examples. That is the goal for today. 2 of the videos are here, part 1 of Le Chatielers and dynamic equilibrium. The other one's going to be on my page, which I'll put up there a little bit later. So here we go. Last class, a little refresher. What do we talk about? Last class, we talked about equilibrium. But before we did that, we talked about kinetics. Topic 1, we talked about rates of reactions. Kinetics. We talked about effective collisions. What's an effective collision? It's got to be oriented correctly, direct hit, but with enough speed. If you don't have enough effective collisions, the reaction is not going to move on to the opposite side. We talked about factors that affected rates of reaction, such as concentration, temperature, pressure, and surface area. We talked about how to speed up a rate of reaction. Increase temp, increase pressure, increase concentration, increase surface area. If you do those things, you have more effective collisions. We talked about factors that decrease rates of reaction. Decrease temp, decrease pressure, decrease surface area, decrease concentration. Those are the 4 factors that would decrease. By now, we should definitely know the potential energy diagram. We should know how to label it. We should know the difference between the exo and endothermic reaction. This is an endothermic reaction. You can see your heat's on the left. You should be able to label that whole thing inside and out. You should be able to look at this little curve right here and say, oh, endo. Reactant slow, products high. You should know where heat is. You should be able to look at a potential energy diagram and say, oh, that is an exothermic reaction. Heat is released. Heat is given off in the reaction. You should know what a catalyst does. A catalyst is something that speeds up the rate of reaction. And we left off last time. I'll edit this once we get to the note packet. We talked about equilibrium. We said equilibrium, the forward and the reverse reaction take place at the same time. The rate is the same, not the concentration. It's going to be the rate is the same. We talked about phase equilibrium, and within phase equilibrium, we said it has to exist when it's going to be vaporizing or melting, heat of vaporization, heat of fusion area. That's where phase equilibrium exists. When 2 phases are happening at the same temp. At that temperature, you have 2 different phases. We also talked about solution equilibrium in terms of saturation. So saturation is a point of solution equilibrium. We'll finish up chemical equilibrium, analyze examples, we'll do all that stuff. But before we do, let's watch this video on equilibrium.
In this lesson, you will learn about dynamic equilibrium, the conditions required for dynamic equilibrium to be reached, and examples of systems at equilibrium. Imagine you are digging a hole. You got it? Imagine, as you are digging that hole, your friend is refilling it. If you are digging the hole faster than your friend, the hole gets larger. If your friend is filling the hole faster than you, the hole gets smaller. But if the 2 of you are working at the same speed, there would be no change to the size of the hole. The same concept can be applied to a reversible reaction. If the rate of the forward reaction, reactants to products, is the same as the reverse reaction, products to reactants, the reaction is said to be at equilibrium. This is called a dynamic equilibrium because both processes are occurring simultaneously, even though there is no overall observable change. For a chemical system, such as a reaction or a phase change, to be at equilibrium, it must meet 2 important criteria. First, it must be a reversible process. Second, it must be taking place in a closed system. A closed system is one where there is no exchange of matter, only exchange of energy. An example of a reaction at equilibrium is the reaction of hydrogen and iodine in a closed container to produce hydrogen iodide. At the start of the reaction, there is a high concentration of hydrogen and iodine, and the concentrations decrease as hydrogen iodide is formed. The concentration of hydrogen iodide increases as the forward reaction proceeds. As hydrogen iodide is formed, the reverse reaction is then able to occur. Over time, the concentrations of hydrogen, iodine, and hydrogen iodide remain constant. So what is happening here? The reaction of hydrogen and iodine to produce hydrogen iodide is occurring at the same rate as the decomposition of hydrogen iodide to hydrogen and iodine. So there are no observable changes, although both the forward and reverse reactions are occurring. This reaction has not stopped, but rather has reached dynamic equilibrium. What would happen to this reaction if the lid on top of the glass jar was opened? Please pause the lesson to think about this and resume when you are done. If the lid was removed, the system is no longer at equilibrium as the reactants and products, or matter, would be able to escape the system. Liquid bromine equilibrates to form gaseous bromine at room temperature. Remember that this is not a reaction, but rather a phase change. Phase changes can also reach equilibrium under the correct conditions. As liquid bromine evaporates, gaseous bromine condenses. Since these two processes are occurring simultaneously at the same rate, there is no observable macroscopic change, but the system is in fact in dynamic equilibrium. In summary, a chemical system is said to be at equilibrium when the rate of the forward reaction is the same as the rate of the reverse reaction. There are no observable changes, but both directions of the reaction are occurring, so it is a dynamic equilibrium.
Okay, so equilibrium can exist when a system is closed. If it's not a closed container, closed system, equilibrium will not be reached. We know that. We talked about phase, we talked about solution. Let's move on forward. Let's talk about chemical equilibrium. So chemical equilibrium, dynamic equilibrium, kinetic equilibrium. Before I get there, let's go up to the top. I'm gonna change my topic numbers a little bit. I'm gonna change topic 6. I'm gonna change this right here. I'm gonna edit it. We already talked about chemical reactions. We already talked about balancing chemical equations earlier in the year when we talked about chemical bonding. So I'm gonna get rid of those. So we're not really reteaching that, but I will review that a little bit later. I'm gonna change this to topic 4A, which is gonna be equilibrium. And then I'm just gonna cut the Chatielers. So that first portion's on equilibrium. It'll make more sense when you see the examples. Example 4A, topic 4A is going to be equilibrium. You'll have an exit pass on 4A, equilibrium. You'll also have an exit pass on Le Chatelier's principle, or examples on Le Chatelier's. I'm just going to add this to a new page. Call this topic 4B, Le Chatelier's principle. And that will go through a little bit later. If you're thinking about that benchmark exam for the end of the quarter, I know it's 5 weeks just ended. That benchmark exam is going to be at the end of the month before spring break. So maybe you want to start preparing. As of right now, it is only for quarter 3 content, which would include solutions and kinetics. and also the heat and phases. So that stuff, the other teachers are teaching phases now, or already just have, and heat will be on there too. But we'll review that a little bit when the time comes. All right, next up, dynamic or chemical equilibrium. I threw dynamic in there too. All right, when reactants are first mixed, you have a chemical reaction. When reactants are first mixed, there's no products formed. So like the reaction I did with the whoosh bottle, I took that 5-gallon jug of plastic jug, not water, there's no water in there. I took that 5-gallon jug and I mixed a couple things. So you saw me do this, had a nice little explosion there. Here's my jug. And then I put some chemicals in there. I just put some methane in there. So I added some methane. There's methane there again. Similar type of reaction. CH4 is methane. We'll know that at the end of the year. And we also mixed some oxygen in there, O2. So in this reaction, the first thing I did, I put some methane in. 20 milliliters of methane. I took some oxygen, which was already in the air, so I didn't really put that in. It was there, but I didn't really insert it in. I took those two things together, and I had to add a catalyst. My catalyst in that situation was the flame. If I didn't have that flame there, that fire there, this reaction would not have occurred. So if I didn't get a little spark of flame there, this reaction would never have occurred. So I added my little lighter there. So heat was added. But if I didn't add the heat, you would never move on to form the products. You would never get the products. Just like this first bullet right here. First bullet says, when reactants are first mixed, there are no products present. Only the forward reaction can occur. So once you add catalyst, then the forward reaction can occur. Only the forward reaction can occur. Examine what happens in the chemical reaction between water vapor and methane. Methane gas plus water vapor. In the reactants, you just mix two things together, the product is not going to form. Once you mix them together, if they react, a product will be formed. At the time, as time progresses, a concentration, what happens here? Why do they react? As time progresses, the concentration of CH4 and H2O will decrease. Let's think about that for a second, because that's going to help us out with the Chatielers examples. You just mix them in, the concentrations are going to be really strong. You just mix in the methane and the oxygen into this whoosh bottle, the concentrations are really strong right in the beginning. What happens when they start to react? They're going to react, they're going to start to dissolve, react with each other, they're going to get more diluted. So as you first mix them, they're high concentration, but as time progresses, the concentration is going to decrease, causing a decrease, causing the forward reaction. So forward reaction goes from reactant to product. As a decreased concentration causes a forward reaction to slow, while the concentration of H2, so these two things react, concentration decreases as time progresses, but then it's going to form some products. So the H2 and the CO would slowly increase its concentration as it reacts. It's producing, it's shifting over to the right. So this is going to be increase of H2 and CO. and causing the rate of the reverse reaction. Oh, wow. Where am I now? Hold on, I'm sorry. Okay, yep. Causing the rate of the reverse reaction to increase. And causing I apologize, folks. While the concentration increases, that's where I made a mistake. Concentration of H2 and CO increase. I made a mistake there. That's why it didn't make sense. Causing the rate of the reverse reaction to increase. Jump on a teeter-totter, what happens? You're gonna go up, you're gonna go down, you're gonna be balanced for a short period of time. It's a constant shift, back and forth, reactant to product, product to reactant, reactant to product, trying to find that balance for equilibrium. As time progresses, the concentration of CH4 and H2O decrease, causing the forward reaction to slow down. While the concentration of H2 and CO increase, causing the rate of the reverse reaction to increase. In this situation, the slowing and the forward down, the decrease of the forward reaction, or the slowing down of the forward reaction, and the increase of the reverse reaction continues until the two reactions become the same. So it's trying to find that place of balance. It's like you want balance in your life. If you don't have balance in your life, then you're gonna go crazy. Find some balance. Hopefully find some balance in this class. Hopefully you figure out the routine. Hopefully you figured out me, my expectations, all that stuff. And last thing, for equilibrium, at this point, equilibrium, chemical equilibrium exists. So whatever this point is here, when you have that balance between both of them, chemical equilibrium is reached. All right, once we're done with that, I'm going to analyze some examples on topic 2B. 4B. I'll leave this open as I analyze the questions. So please open up examples. We'll do these together. 4A. Try it again. 4A. Equilibrium. These numbers are all messed up. So here we go. We're going to do these questions. Again, if you can do these, you should be able to do the exit pass. 8 questions here for examples. They're all related to equilibrium. Starting right there. All right, question number 1. The diagram here shows a bottle containing NH3 dissolved in water. NH3 dissolved in water. How can equilibrium NH3 gas, equilibrium NH3 aqueous be reached? So we're trying to figure out this place of equilibrium. Hi, Joey. We are doing the examples for 4B, equilibrium. All right, this question, here we go. We want equilibrium to be reached. How can it be reached here? First thing, with an equilibrium, the only way equilibrium can be reached, it has to be a closed container, a sealed container. Equilibrium can occur in a system where neither the reactants nor the products can leave. So it has to happen in a closed system. So definitely, what are you going to do here to seal it off? You're going to cap it. You're going to put a cork on this. You're going to add some sort of top. Maybe it's a watch glass, a stopper the bottle. Put a cork on this. No products can leave. Hopefully, then you can see you could have some phase equilibrium there. So again, phase equilibrium goes from, maybe it's going from a liquid to a gas, or maybe it's going from a gas to a liquid. If you have a closed system, equilibrium can be reached. If you don't have a closed system, what's going to happen? It's going to go from a liquid to the gas, and then it's going to say, I'm out of here. It's not going to have equilibrium. It's not an equilibrium. It moves on to the forward reaction. This first question, if you cork the bottle, equilibrium can be reached. Number one, best answer is going to be choice D. Easy one. Cool the contents. What's going to happen is make the particles move slower. Add more NH3 gas. If you add more NH3 gas to it, what's going to happen? Yeah, there's going to be more particles in there, but that also means that there's going to be more particles that escape. If I add more NH3 gas, more of them are just going to say they're out of there. Cool the contents, slows it down. Add more water to that situation. Okay, we have all this water up here. Still going to escape. Equilibrium will not be reached. One, the best answer is B. Number two, which factor must be equal in a reversible chemical reaction at equilibrium? What must be equal for equilibrium? Must be equal for reversible chemical reaction. So it's going from reactant to product is a forward reaction. Reversible is going to be going from product to reactant. Product to reactant. I know sometimes students don't like to see the arrow in their direction. Or product to reactant. Either way. Which factors must be equal for reversible chemical reaction at equilibrium? What do you think for this one? Number two, what must be equal? There you go. I highlighted a little box there. It says equilibrium is a state of balance between the rates of the two opposite processes taking place at the same time. So it's got to be the rates are equal, not concentration. The rates are going to be equal. Rates of reaction, the forward and reverse reaction are equal. The shifting is equal. Concentrations do not have to be equal. They love asking that one. Potential energies aren't going to be the same, nor are activation energies are necessarily not going to be the same. Number two, the rates of reaction are going to be equal. Two, the best answer is D. Next up, number three. Given the reaction at equilibrium, we have CO, 2 moles of CO plus O2 at equilibrium is 2 moles of CO2. Which statement regarding this is always true? So you have this chemical reaction. It looks a little bit different, has this little sign there. Hopefully you know that means equilibrium. Which statement regarding this reaction is true? Is always true. Think about it. Please put your answer in the chat once you derive an answer. You'll see the routine of these questions. Thank you. 3 for 3, 4 for 4, 6 for 6, 7, 8 responses. Thank you. 8 for 8. Cool. So that equilibrium symbol, again, is referring to the rates. The rate of the forward and the reverse reaction are equal at that moment. They're equal. At that moment of the reaction, the rates are going to be equal. No, they do not happen in an open container. It has to be a closed container. Closed. The masses are not going to be equal, nor are the concentrations going to be equal. 3, the best answer is going to be choice A. 3's A. Next up, number 4, a sample of water in a sealed flask at 298 Kelvin is in equilibrium with its vapor. This is an example of what? Think about it. All right, I just drew an example, just a little diagram here. In case you're stuck with a question, you could draw pictures to help you out. Sample of water, sealed container at 298 Kelvin. Okay, so temp's 298. It is a sealed container. And water, here's my water, with its vapor. It's trapped in there. So what's going on? You have liquid transferring over to a gas. You also have, so liquid going to gas. You also have a gas going to liquid. Liquid to gas to liquid. All this is happening in a closed container. Think about maybe a bottle of water, a closed bottle of water. That closed bottle of water is not going to have, you have a brand new bottle of water, never opened. In the summertime, you're going to see like little condensation on the top of the bottle where there's empty space or the gas particles are. And obviously, wintertime, you're not going to see the condensation at all because it's not going to heat up that much. So that's an example of phase equilibrium. So I would draw this diagram. After I draw that diagram, I'd think about what kind of equilibrium is it? There's no such thing as static equilibrium in this class that we're talking about. I would say, oh, water to vapor. I would think of water as being a liquid, hopefully. And then I think about this little curve right here. Solid, heat of fusion, liquid, then gas. This curve is going to be on the benchmark, just so you guys know. And within that, we haven't seen any questions on the curve on the benchmark. This portion right here and this portion are going to be places where equilibrium exists. This situation is going to be specifically here. So it's going to be water at 298 Kelvin, or it's going to be a vapor. So anywhere within that curve, that's where equilibrium is existing. That is phase equilibrium. A lot of you guys picked that. Nice. Phase equilibrium. Solution equilibrium, you're going to see a question maybe about saturation. Chemical equilibrium, it's going to be a chemical equation where both sides are going to be balanced. All right, number 4, the best answer is choice B. Number 5, a system is said to be in a state of dynamic equilibrium when what? Please put the answer in the chat once you come up with an answer. Equilibrium. Awesome. Thanks for the responses, guys. That looks like everybody picked D that responded. Thank everybody. Yep. D, the rate of which the products are formed are the same as the rate which the reactants are formed. If you see a question on the reagents on equilibrium, it's going to talk about the rates. Rates at which the products and reactants are formed are going to be equal. So choice D is the best answer for that. Number 6, given the reaction N2 plus 3 moles of H2 at equilibrium yields 2 moles of NH3 plus 22.0 kilocalories, or heat, energy. When equilibrium is reached in the system, the rate of the forward reaction is, please put in the chat. Thanks, Alex. Kai, thanks. Thanks, Kim. Thanks, Jumila. You're making this topic look easy. They'll get tougher for the next one. Equal to the rate of the reverse reaction. They're going to be equal. The thing that's going to be equal is the rates. The rates are going to be equal. Equal. Choice C, best answer. Number 6 is C. A couple more questions. Which factor must be equal in a reverse chemical reaction at equilibrium? Which one's equal for reversible chemical reaction at equilibrium? Please put the answer in the chat. Yep, the rates of the forward and reverse reaction. Know that concept. The rate of the forward and the reverse reaction are equal. Not the concentration, not the PE, not the AE, activation energy. The rates of the forward and the reverse reaction are equal. Potential energy diagrams. You should be able to look at these curves and say, hey, this is an exothermic reaction. Starts high and gets low. Get low. You should also know this green one would be like a, whoops. This green one would represent a endothermic reaction. Kind of. Equilibrium. This point right here, they shift back and forth. So it goes from situation for like an exothermic reaction. You got the reactant to the products, plus your heat. There's my heat. As it shifts back, shifts on back to the other side, it's going to go from basically the product plus your heat, or reactant plus your heat, yields the other direction a reactant. That point right there of the potential energy diagram would be the point where equilibrium is reached, where they intersect at that point. Don't sweat that little diagram too much. Last one, here we go, number 8. Which balance equation represents phase equilibrium? Different type of question. Phase equilibrium, where's phase equilibrium reached? A, B, C, or D? Please put your answer in the chat. Nice. Phase equilibrium. So my example for phase equilibrium, if you look at your notes to your left, or maybe that little diagram, that diagram, phase equilibrium happens here, or happens here. This would be a heating curve for a substance. So maybe it's a heating curve for water, H2O. You heat water up, starts at maybe -10 Celsius. At 0 degrees Celsius, it's going to freeze. Or you could say at 0 degrees Celsius, it's going to melt. So whatever way you're looking at it, it's going to either freeze or melt. it's still water. So it's water at, this curve is going to be water at the solid or H2O, or it's going to be H2O as a liquid. This equation will be representing right here on the curve. That portion of the curve is right there. It's still H2O, it's still solid or a liquid. Solid there, liquid there. Next portion of the curve right here. What's the equation? It'd be H2O as a liquid or H2O as a gas at equilibrium. Still H2O. Phase equilibrium, it has to be the same element or compound, but the phases must be different. Phases must be different. Choice C is the best answer. Choice D is no difference in phases. Also, the compounds are different. And choice A, no change in phases. Choice B, no change in phases. Best answer is going to be choice C. C is the best answer for number 8. All right, so those are types of questions you might see on equilibrium, topic 4A. If you understood those questions, which it looks like a lot of you guys did understand them, if you understand those questions, the exit pass is very similar to the examples. Little gift for you. All right, moving on forward, we're all done with equilibrium. That's due on Saturday, so please do the exit pass by Saturday. Moving on to Le Chatelier's principle. So what does Le Chatelier's principle analyze? It analyzes, or he analyzed, stresses on systems. He analyzed if we stressed out a chemical reaction, what happened? If we manipulated the concentration or pressure of a gas, or if we manipulated temperature, what happens to the chemical reaction? So that's what he did. He figured out how to stress out chemical reactions at equilibrium, and he wanted to know what would happen to the situation. Let's watch a flick to introduce it, and we'll get to the notes.
In this lesson, you will learn about Le Chatelier's principle, which explains what a system at equilibrium does in response to stresses. Let's return to our original example of you digging a hole and your friend refilling it simultaneously. If you start digging at a rate faster than refilling, the hole gets larger. In order to maintain a constant size of the hole, your friend must work harder to fill it faster. Following on the same idea, when a chemical system at equilibrium is stressed, the system works to restore equilibrium. This is Le Chatelier's principle. The stresses are changes to the concentration of either the reactants or products, changes to the pressure, although this is only applicable to gaseous systems, changes to the temperature. Let's examine a hypothetical reversible reaction at equilibrium where reactant A reacts with reactant B to form product C and product D. If we added more A and B, the system becomes stressed and is no longer at equilibrium. To counteract the stress, the system forms more C and D in order to remove the excess A and B. The equilibrium, therefore, shifts to the right. If we added more C and D, the system becomes stressed and is also no longer at equilibrium. So to counteract the stress, the system forms more A and B. Therefore, the equilibrium shifts to the left. What happens if we remove C and D as they are being produced, or if the concentration of C and D is decreased? Please pause the lesson to think about this and resume when you are done. The system is now stressed and no longer at equilibrium. To counteract the stress, more C and D are produced, so equilibrium shifts to the right. When concentration increases, equilibrium shifts to the opposite side of the reaction. When concentration decreases, equilibrium shifts to the same side of the reaction. Changes in pressure. The stress to a system at equilibrium is only applicable to gaseous systems. For this stress, we will examine another hypothetical reaction at equilibrium, where reactant A reacts with 2 moles of reactant B to form product C and product D. An increase in pressure means that there is a decrease in volume, so there is less space. Equilibrium will shift to the side of the reaction with fewer moles. In our example, an increase in pressure will cause equilibrium to shift to the right, since there are fewer moles, 2 moles compared to 3 moles on the left. A decrease in pressure means that there is an increase in volume, so there is more space. Equilibrium shifts to the side with more moles. So in our example, equilibrium shifts to the left. So an increase in pressure favors the side with fewer moles, and a decrease in pressure favors the side with more moles. In our next lesson, you will learn about how a system works to restore equilibrium in response to changes in temperature. In summary, Le Chatelier's principle states that when a system at equilibrium is stressed, the system works to restore equilibrium.
How are we going to restore equilibrium? That's our goal for class the rest of today. All right, so you guys really don't like to be stressed out a lot. If your friend's yelling at you or mom's yelling at you to clean your room, maybe you'll be stressed out. Maybe you just will brush it off. But typically, you don't like to be stressed. You're stressed. What are you going to do? You're going to relieve that stress. Mom's telling you to clean the room, grandma's telling you to clean the room, whatever it may be, then after a while, you're just going to get sick of it. You're just going to clean the room. Then they're off your back. You get in a relationship, you guys are stressed out all the time. You and your boo just keep fighting all the time. What are you going to do? You're either going to resolve it and talk, or you're going to say, you're not my soulmate. I'm going to find someone new. So once you find a stress, you're going to find a way to relieve it. Again, I told you this before, if you have 5 tests in one day, you're going to be stressed out. What are you going to do? You're going to either A, you're going to study for the test and do well, or B, you're going to say, hey, I'm going to wing it. Whatever it is, it is. Once the test is over, that stress, though, is relieved. Same thing for chemical reactions. Chemical reactions, they get stressed. When they get stressed out by either temp, pressure, concentration, they're going to do something. They're going to try to relieve that stress. Let's figure it out. So that's what Le Chatier did. My goal for today is to get through these notes. Little heads up. We'll go through it. And next class, we're going to take a ton of time to analyze examples. So here we go. Le Chatier's principle, analyzing it. With Le Chatier's principle, that video did a really good job explaining it. You may want to rewatch that one maybe tomorrow or maybe tonight to help you out. So Le Chatier, what did he do? He took the things that affected reactions, such as temperature, pressure, concentration, surface area. No. He took temperature, pressure, concentration, those 3 things that affected the rates of reactions, and he used them to stress out chemical reactions. So any change in temperature, in concentration, or pressure of gases, pressure on gases, pressure does not affect liquids, pressure does not affect solids. It only affects gases. Oh, change my color. Green. Let's go green. Just check my phone to that video. It's 54 degrees out. Oh, it shouldn't be out there. But we have the best class of the day, so I'm more excited to be here with you guys. Any change in temperature, concentration, or pressure on gases on an equilibrium system, has to be at equilibrium, is called a stress. Has to be in a closed container with equilibrium reached. New term for us, stress. A stress is going to be either concentration, temp, or pressure. Le Chatielers principle explains. Describes, explains how systems at equilibrium. Man, some of you guys have like some really cool coloring schemes for your notes. I was really like impressed with them. Sorry, I get excited about those things. Or like the organization of your notes. Some of you guys are doing really well with that. System at equilibrium. Responds to relieve a stress. Get over that stress. To relieve any stress on the system. You take a balloon from the Dollar Tree, you buy a balloon from the Dollar Tree, it gets really hot out, the balloon's going to heat up, those particles inside are going to really move quick. How is it going to relieve the stress? It's going to either explode, expand, or contract. When a system is at equilibrium, if a system's at equilibrium, it's going to have a stress on it. It could have a stress on it. When a system at equilibrium is stressed, I'm going to say, the system shifts, a new term, shifts. So we're talking about shift to the right, shift to the left, move over to the right, move over to the left, whatever it is, it's shift. System shifts. In order to relieve the stress. So it's going to proceed to the opposite side, shift, in order to relieve that stress. In equilibrium. Oh, and restore. And restore the equilibrium. So maintain that equilibrium again. So it's always going to want to try to find that balance. Balance in life. Balance of the reaction. Us during the pandemic, we didn't like to be stressed out. We didn't like that stress when, hey, maybe you didn't realize during the time how bad the pandemic was during like January 1st, like the first wave, and then like January 1st all the way up there. Maybe I'm too much with this stuff. My wife says I'm too much with this pandemic and analyzing these numbers and telling her family to wear a mask out in public or tell whatever. But anyways, it's a pandemic. During this point right here, January 1st, that was a bad time. We were stressed. Society or politicians were saying, hey, not to go and spend holidays with your families. That caused some stress. What happened? People got smart, they wore a mask, and then this pandemic decreased. What's happening now? We're starting to feel a little bit better. We're relieved of the stress because the numbers are lower. Up here, how do we feel? We didn't feel very happy. Some of us were sad, we're home, we're inside. But once that stress is relieved, that the numbers decrease, we feel a little bit better. Le Chatielers principle, analyze stresses on systems. The first stress that we're going to analyze is going to be concentration. So concentration, first stress. We should know concentrations would be molarity. should know it's going to be moles per liters of solution, or solute versus solution. Molarity or concentration. The rates of the reaction can be changed by changes in concentration, temperature, and the presence of a concentration, pressure on gases. So that's a little repetitive. In those notes, it says the same thing again. Just kidding, that was me. At equilibrium, the rates of the forward and reverse reaction are going to be equal. So again, it doesn't say it directly in equilibrium, but when you have equilibrium existing, the rates of the forward and reverse reaction are equal. At equilibrium, the rates of both rates of forward and reverse reaction are equal. Again, you already know that. The concentration of the reactants and products are constant. They're not going to be equal. It's constantly fluctuating back and forth to find that balance, but they're never going to be equal. They're not going to be equal. The thing that's going to be equal is going to be the rates are equal. Let me find an example that's going to analyze concentration. So we can see it now, and then we'll see it again on tomorrow. You don't have to open this up. I'm going to analyze an example for the Chatielers for concentration. Find that balance, concentration. I'll check out number 5 for concentration. So referring to concentration, this is a Le Chatelier's example for stress on a system. Question number 5 reads, given the equation A plus B at equilibrium yields C plus D plus heat. As additional A is added to the system at constant temperature, the concentration of B. I could do that one, but I don't want to do that one yet. All right, I do want to do number 2. Given the reaction equilibrium at constant temperature and pressure, an increase in concentration of A will do something. We'll do what? So let's check it out. This is the chemical reaction. Temperature is the same, pressure is the same, no change there. It's telling you it's increasing the concentration of A. What's going to happen to B or C or D? This situation, we're analyzing just the reactant portion of the reaction. So we're just checking out that right there. We don't have to worry about the product side yet. Focusing on the reactant side of the equation. All right, it's telling you it's going to increase concentration of A. So I'm gonna put some fake numbers in for now, just some numbers to analyze. Maybe 1, maybe there's 1 mole. There is 1 mole of A. There's 1 mole of B. Let me draw a beaker with 1 mole of A, 1 mole of B. Or a closed container. Drawing a beaker again. All right, so there's gases A, there's gas B inside this beaker. It's a closed container, so I'm gonna cap this off. Cover it up, closed, sealed. It's sealed. So in this beaker, I have A, I have 1A, and I have 1B. They're both gases. They're gonna take the shape of the container. You mix them both together, they're going to start to mix. But I have an A and I have a B. If I'm going to figure out percent, if it's a 1-to-1 ratio here, we'll say the percentage. This whole thing equals, this whole volume equals 100%. Therefore, A has to be equal to 50%. And B is going to be equal to 50% as well. So we're going to assume that this is a 1-to-1 ratio, and 50% of this makeup is going to be A, 50% is going to be B. That is referring to that right there. What's going to happen? We're going to increase the concentration of A. So A is going to go from 1 mole to, let's change it to 3. So we're going to increase the concentration. How do you increase concentration? You're going to increase the number of the coefficient out in front. I'm going to say there's 3 A's. I didn't add A more B, so there's going to be 1 B. Second situation, second beaker. Second beaker over here. I love drawing on Zoom now, as you can tell. Here's my beaker, same size beaker, should be. And what's happening here? I have 3 A's. So this situation, I have an A, 1, 2, 3. And I also have a B, 1 B. This whole thing makes up 100%. How many A's do I have? I have 3 of them, which percentage-wise, if we broke them down, that would be 75%. And B, how many B's do I have? I have just 1. Percentage-wise, it's going to make up 25%. What happened to the concentration of B then? So that whole solution, you can see the concentration looks like it was the same, but in response to the solution, it's going to decrease. So yeah, A got bigger, B is going to have to get smaller. We didn't add more B. If one thing gets bigger, the other thing's going to get smaller. That's an example for concentration. We'll analyze more of those tomorrow. So yeah, it's going to get smaller. A gets bigger in concentration. B's concentration is going to have to get smaller. Decrease in concentration of B. If B had a higher concentration, A would get smaller. Flop. It'd flop over. If C got bigger, D would get smaller. If D got bigger, concentration, C would get smaller. We'll talk about those more next time. All right, moving on forward, let's finish up some more notes. Let's get to next stress, which is temperature. Temperature. Next stress on systems, the Chatielers analyze. It's not in order, but next one, temp. Consider the reaction for the production of ammonia. N2 plus 3 moles of H2 at equilibrium yields ammonia. If you don't know what ammonia is, it's on page 2 of the reference table, plus heat. Heat in this situation, energy, heat. Heat is considered as a product if you're analyzing the Ford reaction. Heat is going to be a product in the Ford reaction. Forward goes from left to right. If the temperature is raised, if you increase the temp, the rates of the forward and the reverse reaction, the rates of the forward and reverse reactions are increased, but not equal. That one should be easy for you to know. If you increase the temp, it's going to increase the number of effective collisions. If you have more effective collisions, it's going to make the reaction happen quicker. So increase in temp increases the rate of reaction. It's going to cause more shifting between the reactions. What's that mean? Let's check out an example of what it's going to refer to. Increase in temp. Check out number 3. So don't worry about these now. We're going to go through them again tomorrow. Given the reaction at equilibrium, H2 plus Cl2 at equilibrium yields 2 moles of hydrochloric acid plus heat. The equilibrium will shift to the right when there's an increase in what? So here's a term, shifting for us. Shift. What happens with a shift? It's going to go one way or the other. It could be a shift to the right, or it could be a shift to the left. We want to know shift to the right. But anyways, analyze this example. If we have heat, make the heat 10 degrees Celsius, whatever. I don't care what you put. If it goes from 10 degrees Celsius to 100 degrees Celsius, what happens to the number of particles? Or what happens to the collisions with particles? Temperature increases. You see a temp increase. There's going to be more effective collisions. As you increase the heat, increase the temperature, energy, particles on this side react quicker. As they react quicker on whatever side the heat's on, it's going to cause a shift to the left. As temperature increases, it causes more effective collisions. It causes a shift to the opposite side. It's going to try to maintain balance over here. So what's going on here? So it's like a chemistry party. And HCl, so what happened right here? So in this situation, just take a minute, think about this for a second. HCl, 2 moles of HCl went to this chemistry party. And at this chemistry party, there's a room. There's an HCl and HCl. There's only 2 little molecules there at this party. At this party, it's 10 degrees Celsius. And then what happened is it's a really nice day out, or the thermostat broke in this party, at that party, and now it's going to be 100 degrees. At 100 degrees Celsius, it's really heated up. These particles are moving faster, faster, faster. And it's just going to get so crazy. They're going to move so fast, and then they're going to want to get the heck out of there. So as it heats up over here, it's going to want to shift to the opposite side. It's going to want to try to maintain a balance. It's going to find a balance there. So as that reaction increases, more effective collisions, it shifts over to the left. These particles would react. It would shift over to the right. It's a constant back and forth action, ping pong action between those things. Again, we'll go through more of those examples next time. Next up, running low on time. Principle, last one for Le Chatier's principle is going to be pressure. Pressure on gases. Le Chatier principle, the stress of pressure. If you manipulate pressure, an increase in pressure will favor the reaction towards the side where there are fewer number of gas molecules. Fewer number of gas molecules. And I'll draw my little classic example when I talk about pressure with a piston or a bike pump. We'll think about that for a second. And next up, a decrease in pressure. Will favor the side with a greater number of gas molecules. I know I'm going fast. I do want to play one last video, 3-minute video at the end of class. It's a classic. This is one you want to put like download, put it on your playlist for when you work out before work today. It's a difference maker. And last thing, a change in pressure will not affect the system if there's no gases present. There has to be gases present. In order to have a stress. No gases, it's not going to affect it. And what I'm talking about with gases, again, you guys know this. I'm not going to draw it in again. Make you guys draw it in again at least. I'm talking about two different cylinders, two different chambers. We know what's going on here. So two different chambers, same size. And the first chamber I have piston. A lot of room in that chamber. So below that piston, there's all that space. Second one, there's not much space. The space that I'm talking about is in pink. There's the space I'm talking about. Increase in pressure is going to favor the side where there's a few number of gas molecules. So if I have an increased pressure, I'll represent my little particles. 1, 2, 3, 4, 5. That's an increase in pressure. What's going to happen? These guys are going to have a lot of effective collisions. They're going to want to get out of there, and they're going to want to go to a side where there's more room. Shove you guys all into a closet, there's not much room. You're going to be obviously hitting each other. A lot of collisions. You're going to want to get more space. All right, last thing for today's class, I want to play this video on Le Chatelier's principle. It's a good one. Enjoy it. Le Chatelier's principle, stresses on systems. Enjoy.
To and fro, forwards and back, simultaneous it flows. Reactants becoming products at the same rate reverse goes. It goes forever, system closed. Nothing gets in or out. But once the system's open, you might hear this shout. Stress, shift, changing concentration. Stress, shift, changing concentration. The Chatielers is so much fun. Equilibrium shift for everyone. If you add reactant, collisions more between. It shifts towards the product side. Product increases seen. If you add a product, collisions will improve. The shift is toward reactant side, and products are removed. If the concentration goes down, whichever one you choose, then the shift's the other way, towards whatever you remove. Stress, shift, changing concentration. Stress, shift, changing concentration. The Chatielers is so much fun. Equilibrium shift for everyone. If you raise the temperature, shift endothermically, move away from the side with heat, and you will surely see. If you cool the system down, it's an exothermic shift. Select towards the side with heat, the temperature will lift. If you raise the pressure, the side with less gas will score. If instead you lower P, shift to the side with more. Shift, changing concentration. Stress, shift, changing concentration. The Chatielers is so much fun. Equilibrium shift for everyone. Stress, shift, changing concentration. Stress, shift, changing concentration. The Chatielers is so much fun. Equilibrium shift for everyone.
Watch it again and again and again. Awesome video. That's it for today. We'll pick up on more examples on the shot days next time. Have a great day, guys. Make a decision. Get out. Go for a walk. Bye, guys. Have a good day. See ya. Bye, guys. Have a great day.